Hey everybody, Chapter 5, Lesson Alpha, Part 2. This should say Part 2 on it. We're going to talk today, I want to talk a little bit more about domain and range of the exponential function, as well as I want to get into some applications of exponential functions. So let's take a function, a times b to the x, okay? And provided there are no vertical shifts going on, and that a is greater than 0, right? So there's no vertical reflection either. Okay, so if that's true, the graph of this would have a horizontal asymptote at y equals 0 and would look like that. Or possibly it could have a horizontal transformation, either reflection or some kind of shift going on. But regardless, it would never dip below or even equal y equals 0. Therefore, the domain of any exponential function is going to always be all real numbers. That will always be the case. Now, the range of an exponential function is dependent on its end behavior. Okay, so its horizontal asymptote will be one of the ends of the interval for the range. And in this case, in the black, red, and blue functions, the range would be from 0 up to infinity, or y is greater than 0. Okay, if there was a vertical reflection, potentially then the range would be something to the effect of negative infinity up to 0. Okay, it all depends on the vertical transformations that are going on. So pay attention to that. If you were to see a plus c over here, that would have to do with our y-intercept, which of course would change this value regarding the range, okay? So be very particular with understanding that in its function notation. So what I mean by that is if you get y equals negative 2 times 3 to the x minus 5, right? Negative 2 times 3 to the x minus 5. I don't need to graph that to know what its behavior will look like. Okay, I do know this. There would be a vertical shift down to y equals negative 5, and the function itself would be below that due to the negative value on a. Okay, so then I know that the domain, which won't change, will be all real numbers, and the range would be from negative infinity up to negative 5. Okay, don't include the y, or the y value for the horizontal asymptote. Okay, kind of disjointed there. I kind of went off the cuff, but hopefully that makes sense. Okay, let's get into some applications. And we're going to talk specifically about compounding growth and decay, which can be an interest with banking. It could be in population. It could be in the decay or growth of some kind of material. It comes in multiple forms, but it will come in two specifically general forms, which is growth and decay. Now, with this, we're not going to do a whole lot with this other than just let you know what this means. You'll see more of this in calculus, but the limit as x approaches infinity of this expression, 1 plus 1 over x to the x power, seems kind of insignificant, but it's actually very important. That limit is going to be e to the first, and that e to the first comes from this value 1 here. Okay, that can be seen either on the calculator or it can be proved using calculus. Okay, therefore this is also true then, and notice how r becomes e to the r in this case, where n goes to infinity. Now, why do we do that? Why do we take n to infinity? Well, when we look at this, you'll probably recognize this from higher algebra. This is the compounding interest formula for investing and all sorts of stuff that can be used in finance, where p is the initial principal value, r is the rate, right? So you might get a 3% interest rate. We always write it as a decimal. N is the number of times compounded. I guess we could just call it number of times compounded, typically per year, but it could be otherwise. And T is the number of years or it could be otherwise. So A is the amount that we are left with. So if it's growth, then this value R over N would be positive, right? Because if it's growing, let's say, like we said, 3%, this would be 1.03. Well, actually, it depends on what N is, but if N was 1, right, every year, then we'd get a 3% interest of growth per year. Let's say we had $5,000. I could write that as 5,000 to the, let's say N was 1, and after 3 years, I wanted to know the amount of money that I had. So if I had $5,000 growing at 3% annually would be N equals 1. For 3 years, I would have a certain amount of money left over. So why is this important? Well, what we just talked about is important because you can see that I get 1 plus R over N to the nth power right here. And what happens is when the number of times we compound the investment or the population with growth or decay, as that frequency at which it's compounded increases to an unknown value, for example, population, we can't say, oh, only population increasing quarterly, you can only have a baby on March 1st and June 1st and whatever. No, that's happening all the time. Therefore, this is the model used for continuous growth and decay, whereas this is this formula here is for quarterly, annually, semi-annually, biannually, whatever, right? It happens a finite number of times. It's compounded a countable number of times per year or per unit of time. Okay, so we're going to use these items, these functions, and their formulas to evaluate some practical, real-world word problems. So let's go ahead and get started. Okay, this slide I'm going to do a little bit more talking than I am writing, but let's talk about investments. So let's say we have $9,000, and it's invested in a savings account earning 2.5%. Find the account balance in 25 years if interest is compounded quarterly. Quarterly represents N equals 4. Or continuously. Continuously means we are no longer going to be using the formula 1 plus R over N to the NT power. So with quarterly, I'm going to use this formula. And I'm going to have values for P, which is 9,000. I'm going to have R equals 0.025. I'm going to have N equals 4, and I'm going to have T equals 25. So I've taken a screenshot of my calculator, and in for Y1, I typed this function, 9,000, 1 plus 0.025 over 4 to the 4x, where x is going to be the number of years at which this has been accruing interest. Okay, for continuously, in this case, no bank ever does this. They won't ever do it for you. And it doesn't make that big a difference in money in the long run because we're starting with such a small amount. But we are going to use PERT, P times E to the RT, where R is 0.025 and T is going to be 25. Okay, again, I'm going to plug that function into my calculator. Of course, T, independent variable, is just used as X in my calculator. And then I want to find out what these values are. So I take Y1 of 25 and Y2 of 25, and you'll see I get different values. But that's the amount of money I'd have in that account after 25 years. Okay, let's do another example. Oh, they're here. In this case, I wrote continuous decay. I don't want that there. I just want to talk about a decay model. All right, when the element gains tonium is inactive, it has a half-life of 29 days. If there are 20 units of gains tonium, how many units will remain if it is inactive for 50 consecutive days? So first thing we need to do is write an equation. I need to explain this equation along the way. So the amount of gains tonium left after T hours, T days, will be whatever it starts at times 1/2 to the T over 29. Now I put T over 29 because if I plug 29 in, I would get p times 1/2 to the 1, which means I get half of p. That's how you write a half-life formula. You'll always take whatever the half-life is, put your variable over that number. So if I want to find out, let's see, how many units are left after 50 days, I want to know what y of 50 would equal. So the p-value here is going to be 20. That's the amount we start with.
Can I have these?
Yes, you can have that.
No, all these?
No, not all of that.
How about...
You can have 3 of them. Okay?
No, how about 4?
And then for t, I would plug in a 50. All right, and this is going to calculate how much Gainstonium is left after 50 days. So plugging that function in, the function y equals 20 times 1/2 to the t over 29, I evaluated using my calculator, and I'm going to round out to 3 decimal places. I get 6.054 units of Gainstonium left after 50 days. Now, just a heads up, I could have written this function slightly differently as p times 2 to the negative t over 29. Using properties of exponents, 1/2 is the same as 2 to the negative 1. Okay, so these functions can look and have different bases, but also have the same behavior. So you can see how 1/2 can turn into 2 to the negative 1. Okay, so just something to be aware of as we go through these problems, as well as the rest of the chapter. Okay, so take a look at this problem. It asks whether this is a growth or decay problem. And how would you know? Well, as I look at something in this continuous growth form, right? This is p e to the rt. Okay, if r is greater than 0 in pert form, then it will represent growth. If r is less than 0, that will be decay. Therefore, the fruit flies here, they will be growing. The population of those will be growing by 3% growth. Oh my gosh, Toy Story. Hold on, I'll be back. Sorry about the distraction there. Okay, so let's look at the remainder of this problem. Part A says how many fruit flies are there in the initial population. So the initial population will be the value of p. Therefore, there are 20 fruit flies, or I don't know, it doesn't specify, but maybe there's 20,000 fruit flies. I don't know, that would be pretty aggressive. Okay, so that's our initial value. Let's look at part C. What is the size of the population after 72 hours? So I plug the function q of t into my calculator, and q of 72 is equal to 20 e to the 0.03 times 72, which my calculator spits out a nice answer for me of, I'm going to round to the nearest whole number. I don't think you can have a fraction of a fruit fly. 173 fruit flies. All right, guys, that's part 2 of lesson alpha. Have a great day. Let me know if you got any questions. We'll see you in the next video.